Okay, hello everyone. My name is Infantri Siahaan, and I am a mechanical engineering student in Udayana University. And now I want to presenting my presentation about heat treatment of steel. This is the topic that we will discussion. There are 10 topic from iron carbon system until heat treatment equipment. So the full reference I take for this presentation is from this book, Metalurgi for the Non-Metallurgy Second Edition by Arthur C. Riordan. Okay, we go to the introduction. Heat treatment refers to the deliberate heating and subsequent cooling of a solid metal or alloy using control methods with the aim of altering its microstructure to achieve desired properties. This process occurs at temperatures below the alloy's melting point and is undertaken to modify both the microstructure and characteristic of the material. The capacity to customize properties through heat treatment has significantly enhanced the applicability of metals and alloys across diverse fields, encompassing applications such as automotive and aerospace sheet metal, as well as the manufacturing of razor blades and hardware steels. Okay, the iron carbon system. Steel is primarily composed of iron mixed with a small amount of carbon, which increases its strength. Pure iron is soft and not structurally useful, so adding specific alloying elements can strengthen it through solid solution strengthening. Carbon plays a crucial role in forming austenite, a paste in iron with a specific crystal structure. Iron undergoes change in its crystal structure at certain temperatures, known as transformation temperatures. Carbon widens the temperature range in which austenite remains stable, making it easier to form. With higher carbon content, steel can form an organized lattice structure called face center cubic or FCC at lower temperature. Austenite usually exists at elevated temperatures, not at room temperature, within a specific range known as the austenite region. Austenizing, the initial step in heat treatment, determines the transformation structure that develops as steel cools, affecting its final properties. This process is crucial in both annealing and quench hardening treatment for steel. Carbon exhibits low solubility in ferrite due to the limited space within its body center cubic or BCC lattice for carbon atoms to occupy. However, carbon demonstrates higher solubility in austenite because the larger interstitial space within the face center cubic or FCC lattice can better accommodate carbon atoms. When steel is rapidly cooled or quenched from the austenitic phase to room temperature, a different phase transformation mechanism occurs. This rapid cooling induces lattice distortion, causing the distorted body center cubic or BCC lattice to quickly convert into a new metastable phase known as martensite. The martensite crystals in itself resemble that of BCC, but with one of its edges, referred to as the C-axis, elongate compared to the other two. The structure of martensite is termed as a body center tetragonal or BCT crystal structure. Next is common phase in steels. The first is cementite and pearlite formation. The equilibrium iron-carbon phase diagram applies when temperature is held constant or when heating and cooling rates are slow enough to approximate equilibrium or isothermal condition. The extent and shape of cementite formation depends on the amount of carbon and thermal history, as described subsequently. The discussion centers on the transformation of austenite in steels with three types or levels of carbon alloying, such as the tectoid, hypoeutectoid, and hypereutectoid. Next is martensite. Martensite, as previously mentioned, is a metastable formation that emerges when austenite undergoes rapid cooling. It exhibits an acicular microstructure in both ferrous and non-ferrous alloys. In alloys, where solute atoms occupy interstitial position within the martensite lattice, like carbon in iron, the resulting structure is extremely hard and significantly strained. Conversely, when solute atoms occupy substitutional positions such as nickel in iron. The martensite tends to be softer and more ductile. In the case of steels, the hardness of martensite correlates with the carbon content. The high hardness is due to the fact that the BCT structure of martensite is less densely packed than austenite, and also ferrite to a lesser extent. This results in a volumetric expansion at the MS temperature and lattice distortion, which provides strength or hardness by impeding dislocation movements. The microstructure of martensite in steels has different morphologies and may appear as either lead martensite or plate martensite in this picture. Plate martensite, as the name indicates, form as lenticular or lens-shaped crystals with a zigzag pattern of smaller plates. Next is bainite. Bainite is a distinct metastable phase in steel that forms when cooling rates are not rapid enough to produce martensite, but still prevents sufficient time for carbon diffusion to form perlite. Similar to perlite, bainite consists of ferrite and cementite paste. However, their shapes differ significantly. While both perlite pastes have a lamellar structure, ferrite in bainite exhibits an acicular morphology, and the carbides are distinct particles. These morphological disparities lead to contrasting property characteristics between bainite and perlite. Generally, bainitic steels offer high strength along with good toughness, whereas perlitic steels possess high strength but exhibit poor toughness. So, we can see in this picture where is bainite and perlite. Seems like the same structure here, but bainite is more toughness from perlite. Yep, we can see where the bainite is, and this is the perlite form. Next is critical temperatures and transformation diagrams. Critical temperatures of steel define either the onset or completion of a phase transformation. There are three important critical temperatures in steel heat treatment, such as A1, A3, and ACM. A1 is critical temperature for the start of the transformation to austenite, and then A3 is critical temperature for complete transformation of the alpha plus 2 phase mixture into 100% austenite. The next ACM is critical temperature for complete transformation of the G plus Fa3 two-phase mixture into 100 austenite. The kinetics of phase transformation hold equal significance as the equilibrium diagram in the heat treatment of steels. Practical heat treatments involve heating and or cooling process. These transformation diagrams play a crucial role in steel heat treatment, depicting phase transformation concerning temperature and either time or the rate of temperature change. In general, there are 4 different types of transformation diagrams that can be distinguished. These include isothermal transformation diagram, isothermal transformation or IT diagrams, continuous heating transformation or CHT diagram, and continuous cooling transformation or CCT diagram. CCT or continuous cooling transformation diagrams are highly valuable as they account for cooling rates, which are crucial in quenching or cooling procedure. These diagrams can also incorporate cooling rates concerning section size and the cooling medium used. This enhances the practical applicability of CCT diagrams by considering factors like part thickness and cooling medium. Moreover, computer simulations are increasingly effective in modeling phase transformation. Okay, the next topic is annealing and normalizing. General annealing thermal cycle. Annealing cycles are varied according to the temperature and the method of cooling used. Annealing temperatures may be classified as subcritical annealing, intercritical annealing, and supercritical annealing. Supercritical annealing to achieve full austenitization of either hypo or hyper-educted steel. So we can see how steel in this cycle, like annealing, subcritical annealing, intercritical, and supercritical. So this is the graphic that means full annealing of the iron. Annealing guidelines. The metallurgical principles of annealing cycles can be described by the following 7 rules as mentioned below. Rule number 1. The more homogeneous the structure of the austenite steel, the more completely lamellar will be the structure of the annealed steel. Rule 2. The softest condition in the steel is usually developed by austenizing at a temperature less than 55 degrees Celsius above A1 and transforming at a temperature less than 55 degrees Celsius below A1. Rule 3. Because very long times may be required for complete transformation at temperature less than 55 degrees Celsius below A1, allow most of the transformation to take place at a higher temperature, where a soft product is formed, and finish the transformation at a lower temperature, where the time required for completion of transformation is short. Rule 4. After the steel has been austenized, cool to the transformation temperature as rapidly as feasible in order to minimize the total duration of the annealing operation. Rule 5. After the steel has been completely transformed at a temperature that produces the desired microstructure and hardness, cool to room temperature as rapidly as feasible to decrease further the total time of annealing. Rule 6. To ensure a minimum of lamellar perlite in the structure of anneal 0.70 to 0.90% Celsius tool steels and other low alloy medium carbon steels preheat for several hours at a temperature approximately 28 degrees Celsius below the lower critical temperature or E1 before austenizing and transforming as usual. Rule 7. To obtain minimum hardness in anneal hyper-extruded alloy tool steels, heat at the austenizing temperature for a long time, approximately 10 to 15 hours, then transform as usual. Next is furnace heating and induction heating. The heat treatment of steel encompasses a broad range of techniques including annealing, normalizing, hardening, and tempering. Furnaces, powered by either fuel or electricity, come in various configurations and are utilized with different media. They are also employed for thermochemical processes like carburizing and nitriding. Induction heating is another significant method offering energy efficiency and faster heating rates compared to traditional furnace methods, as well as other heating processes. Induction heating finds extensive use in heat treatment, particularly for surface hardening of steel and cast iron. Additionally, it's applied to various other treatments such as annealing, normalizing, through hardening, tempering, and stress relieving across a diverse range of workpieces. Okay, next is hardening and tempering. Hardening of steels involves a 3-step process: austenization, quenching, and tempering. Sometimes, an additional step of cold treating is done at low temperatures below the molten side finish temperature of the steel. The quenching process is the rapid cooling of metal from its austenitizing or solution treating temperature, usually between 815 to 870 degrees Celsius for medium and low carbon steel to high temperatures such as 1232 degrees Celsius for high speed steels. Quenching is used to produce martensite in the metal microstructure. The rate of heat extraction by a quenching medium and the way it is used substantially influence quenching performance. Variation in quenching practice have resulted in the assignment of specific names to some quenching techniques, like direct quenching, time quenching, selective quenching, spray quenching, fog quenching, and the last is interrupt quenching. Next is heat treating equipment. Hardening of steel involves a 3-step process of austenization, quenching, and tempering. Sometimes, an additional step of cold treating is done at low temperature below the martensite finish temperature of the steel. This ensures the true martensite transformation and the minimization of retained austenite. Quenching refers to the process of rapidly cooling metal parts from the austenizing or solution treating into temperature, typically from within the range 815 to 870 degrees Celsius for hardening medium and low carbon steel to temperature as high as 1232 32 degrees Celsius for hardening specific grades of high-speed steels. While stainless and high-alloy steel may be quenched to minimize the presence of grain boundary carbides or to improve the ferrite distribution, most steel, including carbon, low alloy, and tool steel, are quenched to produce controlled amount of martensite in the microstructure. Okay, so heat treating equipment is the last topic in this presentation, and yeah, I'm sorry if I tell you how bad I tell you about my presentation, but I say thank you for your attention and see you in the next topic. See you later.